Hello everyone. In this video, I'll explain about the function table, characteristic equation, and excitation table for the four flip-flops. Okay, so we'll start with the first one, that is SR flip-flop. So first we'll write the function table for this. So function table means I have S and R and the output Q and its complement Q bar. Since I have two inputs, I'll have four combinations. Okay. So for SR flip-flop, when the inputs are 0, 0, there's not going to be any change in the output. Okay, so NC stands for no change. No change. Whatever was the previous output, the same value will be retained as it is when the inputs are 0, 0. Now, if the S is 0, R is 1, you should know that SR stands for set reset. Okay, S is set, R is reset. If I am making set value 0 and I'm selecting reset value, that is R as 1, I'm trying to reset the flip-flop. Okay. So reset means output will be 0 and its complement will be 1. So when S is 0, R is 1, this will be called as reset state. Similarly, if S is 1 and R is 0, I'll be making the output 1, its complement 0. We call this as set state. Okay. If S is 1 and R is 0, this becomes set. And if both are 1, I will be getting Q and Q bar both as same, which is not valid. So in SR flip-flop, if I make both inputs 1, 1, it is called invalid state or indeterminate state. Okay. So this is the function table. We call this as function table of SR flip-flop, which has two inputs and Q is the main output where Q bar is just its complement. Okay. Now coming to the characteristic table. So how do we write the characteristics table? So in characteristic table, you will be having the first input is going to be present state Qn. Then you have inputs S and R. And the output is going to be the next state Qn plus 1. Okay, these are your inputs and this will be the output. Characteristic table is currently you have some output and your inputs are ready and you have to see what is going to be the next output for this input. Okay, currently the status is, for example, set, and I am giving S and R values as 0, 1. What will be the next output? Okay, you're predicting what happens next based upon the knowledge of what is there present and what are the inputs you have. Okay, so the prediction of next output is the characteristic table. Now, if you look at the inputs, you have three inputs here. So if you have three inputs, you'll be having 8 combinations. Okay, so 8 combinations are there. Now I have to write the output. Presently, I have 0. Present output is 0. SR values are 0. If SR is 0, there is no change in the output. So whatever I have in the present output, the same thing continues for the next also because S and R values are zeros. Okay. For the next condition, S is 0, R is 1. When you make S0, R1 default, irrespective of what is there in the present condition, my output will become 0 because I'm trying to reset based upon this condition. Exactly in the same way, if I give S as 1 and R as 0, I have to default write 1 in the next state because this combination will set the output. Okay. And if both are 1, 1, I know it is an invalid state. I'll make it X. It can be a 0 or a 1. Next, if I have 0, 0, there should not be change in the output. So whatever was there previously, I'll write the same value. If it is 0, 1, reset. If it is 1, 0, set. If it is 1, 1, invalid. Okay, so you got the output table now. You put 3 variable K map for this. Draw the 3 variable K map because you have to get the equation for this Qn plus 1. That is the characteristic equation. Okay. So QN SR 0 0 0 1 1 1 1 0. S bar R bar S bar R S R S R bar 0 1 QN bar and QN. So look at this QN table. You have 0 1 2 3 4 5 6 7. So for 2 you have 1. Then for 3 it is X. 4 is 1. 5 is 0. 6 is 1 and 7 is X. So if I have to map, I'll be getting two groups in this. One is the quad, other one will be a pair. Okay, so from this I get the answer as the next state value will be, for the quad I'll get the equation as S plus, for the pair I'll get the equation Qn into R bar. Okay, so this is called the characteristic equation of SR flip-flop. So if they ask you to derive the characteristic equation for SR flip-flop, then you have to write this table where you have three inputs Qn, present state SR, and one output, that is Qn plus 1. Then you have to draw the K-map, simplify it and get this equation. Okay, so this is the characteristic table and characteristic equation of SR flip-flop, where you are trying to predict the output, next output, based upon the SR values and present output. Okay. Now coming to the last table of SR flip-flop, it is excitation table. And for this, the input will be present state, next state, and output will be SR. Okay, you can also write this as Qn plus 1. Okay, I've written Q and Q plus. This is present state, this is next state, and these are values of S and R. In excitation table, what you are trying to find out is, I have currently 0 and next it is becoming 1. So for changing the 0 to 1, what should I pass the input S and R values as? Okay, you're trying to find out what is the value of input to change the Q value to Q plus value. Okay, I want to change 0 to 1. So if I want to change 0 to 1, what should I give to S and R? So I'm trying to find out inputs here. I'm trying to find out the values of inputs, that is S and R, based upon the knowledge of present and next value. Okay. So we'll write the combinations first and then I'll tell how to write the SR value for this. Okay. So now for the first combination, that is 0, 0, I have present state 0, next state is also 0. Okay. Now what are the values of S and R which can give me this type of answer? So if I have 0, 0 as SR value, it means no change. Present is 0, next is also 0. So it might be because of no change condition. Correct? There is one more reason for which I can get the output as 0, and that condition is 0, 1 or reset. Even if I reset the flip-flop, I will still get the output as 0. So I have two options to get the output as 0. Either it was because of no change, it kept the previous value, or it was because I reset the flip-flop, so it is again becoming 0. Right? So I have two options for getting output as 0. And in this two option, the one which is same should be written as it is. The one which is changing will be replaced with X. I hope this is clear, right? So next condition is 0, 1. I have present 0, next 1. If whatever was 0, if it has to become 1, there is only one possible combination for that. Only by setting the flip-flop, I can make 0 as 1. So my S value should be 1 and R value should be 0, so that I can change the 0 to 1. Similarly, if I want to change 1 to 0, I should reset the flip-flop. Okay. Now the last option, 1, 1. Present is 1, next is also 1. So possibility is either because of no change or by set option. Also, I can get the output as 1. the previous value was kept as it is, it can be because of no change. Or I am getting the value as 1 because I have set the output. So I have two options here. So what is not, which value is not changing here? R is not changing and it is 0. Whereas S is changing, so I'm replacing it with X. Okay, so I hope this is clear now. When you have two options, no, please check how many options are there to get this kind of transition. And based on, and in those options, which value is constant, keep that as it is, which is changing, replace it with X. Okay, so this is the excitation table. If I have to write the equation for S and R output, since it is only two input Q plus, you will be having a two variable K map here for each output, that is S and R. Here you have Q plus 0, 1. So Q plus bar and Q plus 0, 1, Q bar and Q 0, 1, 2, 3. So here is 0. For 1, I have this 1. 2 is not there. 3, I have X. So if I group it, I'll get a pair. So for S, I have the equation as the next state value Q plus. Similarly, if I draw one more two variable K map to get the equation for R, for 0, I have X, 1, 2, 3. Okay, so I have this. Sorry, 1 second. For 0, it is X. For 1, I don't have any number. For 2, I have 1. For 3, it is 0. I'll get only this pair. So equation for R will be Q plus bar. So these are the two equations you're going to get for S and R. This is the excitation table. Okay, so these are the three tables you have for SR flip-flop: function table, characteristic table and its equation, and excitation table. You need this excitation table to solve or to design synchronous counters. So similarly, we'll try to do for the remaining three flip-flops. The second, I'll take D. So first one is function table. I have D, Q, Q bar. For D flip-flop, it is very simple. Only one input, so two combination, 0 or 1. So if the input is 0, output will also be 0. If input is 1, output is also 1. So here you can just remember it as, for D flip-flop or data flip-flop, the output will be exactly same as input. Whereas Q bar is just complement of Q. Okay. So this is the function table for D flip-flop. Next, if I want characteristic table for D flip-flop, the input is going to be present state and D value, whereas output is going to be next state. 0, 0, 0, 1, 1, 0, 1. Now, when you're writing the output for the next state in D flip-flop characteristic table, you don't have to look at the present state. Directly just copy paste whatever is there in D to Qn plus 1. Because you know, if D is 0, next value should be 0. If D is 1, next value should be 1. Okay, so your output, like next value, will be exactly same as the input. Okay, so directly you can say that Qn plus 1 is same as D. You don't have to put any K map and draw this. Directly you can say that Qn plus 1 is exactly equal to D. So it's very simple for D flip-flop. Okay, now coming to the excitation table for D flip-flop: present state, next state, output D. Oh, 0, 1, 0, 1, 1. So exact whatever explanation I gave you here, whatever is the input, same thing goes to the output. Follow the same instruction. Whatever is your next value, the same thing will be there in the present input also. So don't look at the present state, only take the next state value, copy paste it. Okay, so directly I can say D is exactly same as the next state. Qn plus 1 and Q plus both are same, next state values. Okay, so that's it for D flip-flop: function table, characteristic table, excitation table. Right, now coming to the third one, JK. So function table, if I take J, K, Q, Q. Have 0, 0, 0, 1, 0, 1. So if compare JK and SR, the first three are exactly same as your SR. Okay. For 0, 0, no change. This is reset. 1, 0 is set. Only the last one changes. For SR flip-flop, when it was 1, 1, you wrote invalid. But for JK flip-flop, when it is 1, 1, it will be called as toggle state. Toggle means whatever was a Q value previously, next time when you write it, complement it. If your Q value was 0, now when you write, the Q value should become 1. Okay, so that is toggle state. If I have to now write the characteristic table for JK flip-flop, have present state, J, K values, and the next state. So in this case, you'll be having 3 inputs. So 8 combinations will be there. Okay. And to get the next output, if the JK values are 0, it means no change. So whatever was there previously, write it as it is. If JK is 0, 1, reset. If it is 1, 0, set. If it is 1, 1, toggle. Whatever was there previously, complement it. It was 0, so now write 1. Again, 0, 0, no change. Write this value as it is. 0, 1, reset. 1, 0, set. 1, 1, toggle. If it is 1, complement and write it. That's all. Okay. So for this, again, you have to put K-map now to simplify and find out the equation for Qn plus 1. 1, 2, 3, 4, 5, 6, 7. So Qn, J, K. 0, 0, 0, 1, 1, 1, 0. J bar, K bar, J bar, K, J, K, J, K bar. 0, 1. Qn bar and Qn. So we 1, 2, and 3, 4, 5 is not there, 6. So here you can group this to one pair and this as another pair. So you will get Qn plus 1 as, so from here to here, it is going to be Qn into K bar plus Qn bar into J. Okay. So this will be the characteristic equation for JK flip-flop. Now coming to the excitation table, present state, next state, J and K. 0, 2, 0, 1, 0. Now I have present 0, next is also 0. That can happen if there is a no change option or if there is a reset option. Correct? So I can get the output as 0. If it was no change also, the 0 would be 0 only. If it is reset also, I'll get the output as 0. So I have two options for this change. So which is not, which is constant here, J value is constant, that is 0, whereas K value is changing, so X. Similarly, present is 0, next is 1. This can happen if I set the output or if I toggle. 0 can change to 1 if I toggle it, or 0 can change to 1 if I set it. So I have two options where J value is fixed at 1, whereas K value changes. 1 is changing to 0. 1 can change to 0 if I reset it, or 1 can change to 0 if I toggle it. So again, two options. J is changing X, K value will be 1. Whereas for the last one, 1 changing to 1. No change, that is 0, 0, or set. Okay, again, this is how you write the excitation table for JK flip-flop. So if I have to find out the equation for J and K, take two variable K map, 0, 1, 2, 3, Q and Q plus 0, 1, 2, Q, Q plus 1, Q, 1, X. So we getting J value as Q plus. Similarly, you can do for K. For K, 0, 1, 2, this will give you Q plus. Okay. So this is the excitation table for JK flip-flop. So now coming to the last flip-flop, that is T or toggle flip-flop. The function table is very simple. Input T, outputs are QQ bar. The two inputs are there. When T is 0, there is no change in the output. And if T is 1, there is going to be toggle. If T is 0, just like JK0, no change. JK1, toggle. So T0, no change. T1, toggle. Okay. Next characteristic table, present state, T. And next state, 0, 0, 0, 1, 1, 0, 1. If T is 0, no change, so previous value will be written as it is. If T is 1, toggle, so previous value should be complemented. T0, no change, same one. If T is 1, toggle, so previous is complemented. Okay. Now if I write the equation for this, corresponding equations, values wherever you are getting output as 1, Qn bar into T plus Qn into T bar. So I can write the equation as Qn XOR T. This is the characteristic equation for T flip-flop. Now coming to the last, that is excitation table. I have Q plus present and next state, the output T. 0, 0, 0, 1, 1, 0, 1. So here 0 is 0 only. Present is also 0, next is also 0, no change, 0. Present is 0, next has become 1, toggle. 1 has changed to 0, toggle. 1 is 1, no change. Okay. If there is no change, put 0. If there is a change, put 1 in the output. So equation for T will be, wherever you have 1, take the corresponding equation. Q bar into Q plus Q into Q plus bar. So your T will be Q XOR Q plus. Present state XOR next state. Okay. So this is the excitation table for T flip. I hope all the four flip-flop tables are clear. Function table, characteristic table with its equation, excitation table with its equation. Thank you.